Hi, this is Mrs. Weethy, and we're back for Unit 2, video lesson number 6. So let's get started with that. In video lesson number 7, we learned about Rutherford's model. And with any model, we have questions. And two questions that come to mind are, how are electrons arranged in that empty space? And second is, why are electrons not pulled into the nucleus of the atom? Because when you think about it, electrons have a negative charge, protons are positive, so you would think natural attraction between negative and positive charge, the electrons would be pulled into the nucleus. And if that happened, matter wouldn't exist, but it does. So we need to figure out why that actually occurs. So in the early 1900s, scientists observed that certain elements emit visible light when heated with a flame. And if you think about that, if you take iron and you put iron in a flame and you heat it, it turns red, and then right before it actually melts and turns white. And so scientists were curious about this. The analysis of this behavior showed that there was a relationship between an element's chemical behavior and the arrangement of the electrons in the atom. But because these elements emit visible light, we need to investigate what the relationship is between light, energy, and electrons. And so that's what we're going to do first. We have the wave nature of light, or the wave model of light, in which visible light is a form of the electromagnetic radiation, which we're going to abbreviate EMR. Electromagnetic radiation is any type of energy that travels in waves through space. Other forms of electromagnetic radiation include gamma rays, X-rays, radio waves, microwaves, UV rays. These are all familiar different kinds of electromagnetic radiation that you might know of. Visible light is just a small spectrum of that. This is the entire electromagnetic spectrum. It includes all the wavelengths of energy, wavelengths of energy, any energy that travels in waves. And we have radio waves, which actually are our longest wavelengths. And then we have our gamma rays here at the other end of the spectrum, which are our shortest waves. And then right, not quite in the middle, we have the visible light spectrum. That's the light that we can actually see. It's a very, very small part of the electromagnetic spectrum that includes all of the electromagnetic radiation. And as we're going to learn, we have a relationship between the wave energy, the wavelength, and the frequency of those waves. There are three characteristics of waves that we're going to consider. One is wavelength, and wavelength is the distance between peaks. Okay, and so we have a continuous wave right here. And so wavelength is the distance between two peaks, or the distance between two troughs, because they're going to be the same. Wavelength, the symbol for wavelength is the Greek letter lambda. And when you write it, you'll write it kind of like this, like a slanted line and a little curly hat. So that's the Greek letter lambda, and we're always going to use those symbols. Now the unit for wavelength is a linear unit, meter for those long waves, and nanometer for the shorter wavelengths. It's usually either or, meters and nanometers. Now the second is the frequency, and the frequency is the number of waves that pass a reference point in a second. So if I just kind of draw a wavelength here, you have to imagine these are all the same. Let's say that this is our reference point. So in a second, we would count the number of waves that passes that reference point, and that would be our frequency. Now, the unit for frequency is waves per second, so that's the number of waves that passes in a second, which is also seconds to the negative first, which written would be like this, 1/2. Because we don't usually, you would usually put waves over seconds, and waves isn't really written in our unit, so it's 1/second or second to the negative first. And then the common name for frequency, or the common unit for frequency, is called the hertz. And anytime you're given hertz in a problem, you want to write the unit like this, 1/second, rather than a hertz. Now, the symbol is the Greek letter nu, which if you write it would kind of look like that. Okay, so the third then is that all electromagnetic waves travel at the same speed in a vacuum. But this can vary through mediums like Jello. So if you had a very thick medium, then the wave would actually travel at a slower speed. But the third characteristic is the speed of a wave, which is equal to the speed of light. And the speed of light is equal to 3.00 times 10 to the 8th, and the unit is meter per second. Now, it's given the symbol C. That's a constant, and anytime you see a lowercase c, it always refers to the speed of light. It's a constant, so it's always going to be the same number. Now, we have a relationship between frequency and wavelength, and that relationship is indirect. And what is meant by that is when one of the variable increases, then the other variable will decrease. So if we double one, then the other one would be cut in half because it would be indirectly proportional to one another. So consider this. We have wavelength A, and we're going to take wavelength A and we're going to reduce it. We're going to shrink it up. We're going to shorten it to wavelength B. This red line is going to be our reference point. So when we take this long wavelength and we shorten it, now we have increased the frequency. So you decrease the wavelength, but you increase the frequency. And why is that? Because you're having more wavelengths past this point in a second. So longer wavelength, we're going to shorten it, decrease the wavelength, but increase the frequency. And I have that written here. So wavelength A is longer than B, thus you have less waves of A past the reference point than B. A has a lower frequency, B has a higher frequency, even though the waves are shorter. So it's an indirect relationship. Decrease the wavelength, increase the frequency. If you increase the wavelength, you're going to decrease the frequency. So it works just opposite of one another also. Okay, we have what is called the electromagnetic wave relationship. And in this relationship, we have the speed of light is equal to the wavelength times the frequency. Remember that c is the speed of light, and that's a constant. Lambda is the wavelength, and u is the frequency. And we're going to use this relationship to solve some problems. So let's take a look at this first problem. Microwaves are used to cook food and transmit information. What is the wavelength of a microwave that has a frequency of 3.44 times 10 to the 9th hertz? We're going to use the frequency wavelength relationship equation to solve the problem. Let's write our given and unknown first and the plan, which is simply the equation. So our given is 3.44 times 10 to the 9th hertz. Now, we're going to write hertz rather like this, 1/second. Okay, the unknown is lambda, the wavelength, and the plan is simply the equation. But we're going to rearrange the equation to solve for lambda because that's what we want. And in order to do that, we have to divide each side by nu. So nu divides out on this side. And so what we get is lambda is equal to speed of light over nu. Let's put in our numbers. Okay. And we see that seconds is going to divide out. And that's going to leave us with the number, or the meters in a wave. I'm going to stop this here for a second so that we can calculate. Okay, and if we do the math, take 3.00 times 10 to the 8th, divide by 3.44 times 10 to the 9th, to three significant figures, because we have three sig figs in 3.44, we get 0.0872 meters. And we don't need to put per wave because we're looking for the wavelength, so it's meter that we're just looking for, 0.0872 meters. Okay, let's take a look at one more problem. The red-colored lights in fireworks might be produced when strontium salts are heated. What is the frequency of such light with a wavelength of 6.50 times 10 to the negative 7th meter? We're going to use the same equation to solve the problem. Our given, unknown, and our plan, remember the plan is the equation, our given lambda, use the symbols. So wavelength is lambda, is equal to 6.50 times 10 to the minus 7th meter. The unknown is the frequency, and our plan, C, is equal to lambda nu. Now this time we're going to solve for nu. So we're going to divide each side by the wavelength, which is lambda. And so the equation we're going to work with is nu is equal to speed of light over lambda divided by the lambda. Plug in your numbers. So we're going to take 3.00 times 10 to the 8th meter per second, divide by 6.50 times 10 to the negative 7th meter. Meters divides out. And again, to three significant figures, our answer is 4.62. Okay, it's not writing. There we go. 62 times 10 to the 14th, 1 per second, okay, or hertz. Now you can write hertz as your unit, as your answer, okay? That's it for this video lesson. This is Mrs. Wheathy until video lesson number 7.